Well, welcome everyone. I just want to give a big thanks to everyone at AWS for having me here. I'm really excited to talk to you guys today about building an autoscaling CI cluster. Today we'll go through some real-life examples about how Gusto CI has evolved over the years and how we ultimately ended up at the solution we have today built on top of AWS tooling. At the end of this talk, you all will also have a good idea of some services and tools to look into to build something like this in-house at your own company. So my name is Nikhil Matthew. I'm an infrastructure engineer at Gusto. I lead the developer tooling team. I worked as a product engineer at Gusto for several years and kind of got first-hand experience in how our development philosophies have evolved and how that has changed. And about a year and a half ago, I started our first team that was in service to the wider engineering team at Gusto, mainly working on tools to help development experience be faster, better, and safer. Today, we're a very leveraged team of 4 people supporting an engineering team of over 120. And we handle everything from code authoring tools to testing and build tools, deployments, and getting feedback about your code once it's been launched in production. For me, personally, I'm really passionate about enabling developers to ship faster and ship more securely. So I'm thrilled today to talk to you guys about one of our most leveraged projects we've had at Gusto as a part of this team. When I'm not working on developer tools, you can usually find me playing jazz and blues guitar, hiking, or snowboarding in nearby mountains. So I'll be at the startup bar after the talk today. So if you guys want to talk about tooling or any of those other topics, I would love to meet you and chat. So for those of you who don't know, Gusto is a payroll benefits and HR company, and we focus on empowering small business owners to focus on what they love, which is running their business. So we automate all filings, tax payments, and onboarding forms so you can be sure that you're staying compliant. We serve over 60,000 businesses across America. We pay hundreds of thousands of employees each year, and our system moves billions of dollars annually through our system. We're mostly a Ruby on Rails shop, and like many of you here, we have a monolith that has evolved as our product has grown over time, with several supporting services that have come up over the years. Gusto engineers work on code that people's livelihood depends on. Making sure your benefits are in place or you're getting your payroll on time can be a really important thing for most people, and we take that responsibility really seriously. We firmly believe in moving fast and breaking nothing. We deploy to production several times a day across all of our applications, and we lean really heavily on our CI system to know that when we make a change that we're not inadvertently breaking something in another part of the system. So what is continuous integration? This is probably familiar to a lot of you all here, but there was a great snippet about what continuous integration is and what it gives us on AWS's Code Deploy homepage. So continuous integration is a software development practice where developers regularly merge their code changes into a central repository, after which automated builds and tests are run. The key goals of continuous integration are to find and address bugs quicker, improve software quality, and reduce the time it takes to validate and release new software updates. So what does this look like at Gusto? So we use GitHub as our SCM provider, and all of our production apps have a default development branch. This branch is green at all times. It's always considered our deployable branch, and is always the most up-to-date with the changes we have that will be sent out to staging and then production. So when an engineer goes to work on their feature, they'll branch off of development, and they'll check out their feature branch. They'll start working on their feature and commit the changes there. Once they're ready to push those changes up, we'll automatically run the entire suite of tests in CI, and the engineer will get a Slack message with their test results. At this point in time, they can fix any tests that they may have broken and iterate on that feedback until they get a green build. At that point in time, the code review will be passed off to another member of the team, and once everything looks good, it's good to merge into development. Once the changes land in development, we'll run and test one last time to make sure that it integrates with the most upstream changes, and then we'll send it out to staging for verification, and at that point, we're ready to deploy. To get a sense of how often we're doing this and how many times this is happening, we have about 120 contributors doing this every single day. We're running about 600 builds across all of our applications, and we deploy about 40 times a day across all of our services. So I like to think about CI in 2 portions, the scheduler and the compute. So the scheduler is what talks to your SCM provider, listens to things like Git pushes, and creates a workload based on the changes that you've pushed up. Usually this workload is defined in a configuration file that lives in your repository. For example, in a Ruby application, you might have a configuration file that says, I need to run all of my tests in the spec directory across Ruby versions 2.3 and 2.4, and the scheduler will create that workload to be picked up by the compute. So the compute is usually a set of virtual machines that actually run your software. So these workers poll the scheduler for work that's waiting to be completed, and they're usually provisioned with whatever software you need to run your tests. This could be particular Ruby versions, Python versions, version of your database, whatever you need to actually execute your tests. Depending on what provider you use and how you've set up your CI system, these could be machines that you host and you control, and that you have full control over the software that's run on them. Or in the case of a managed provider, it's provided by your CI system, and you have custom setup hooks you have to install any dependencies you might need. So probably the CI system people are most familiar with is Jenkins. This is an example of an unmanaged provider. So in Jenkins' case, it's a self-hosted system, so you're running it on your own infrastructure. It's open in the sense that you have access to the source code and can modify and make changes as needed. And while it's a bit dated, it's supported many large companies at scale and has been around for quite a while. A few years back, when Gusto was less than 10 contributors, we had 100% of our CI running on a Jenkins machine. There was nothing special about this setup. It was running on a machine that sat in our closet. This machine was actually very critical to our business workflow at the time. It would poll our SCM for any changes that came in, and when it did, it would run a build that we had where we manually parallelized our tests across all of the cores on the machine. Jenkins was like our pet. We named him Leroy. He was totally irreplaceable. We couldn't reproduce it even if we wanted to. The machine was set up by SSHing onto the box, running a bunch of ad hoc commands, and we even named him Leroy. So one day, we took about 12 hours for us to get our test results back. At this point in time, it was peak season for Gusto. This is end of year when we're handling tax filings, and customers are calling in to make sure that all of their ducks are in a row. And this was really destructive to our development workflow. So we weren't able to ship any fixes that we had to get out in that time because we couldn't get a positive CI status on the commits that we were trying to send out. And ultimately, we knew that at that point in time, we didn't have the time nor the expertise to build a more cost-efficient, scalable solution in-house. So in order to kind of bring us to the next stage of Gusto engineering, we decided to look elsewhere for a managed provider. So managed providers are usually multi-tenant systems. They're usually hosted on internet outside of your own VPC. These systems are usually closed. You don't have access to customize the software on those systems. Most CI providers do usually provide some hooks, so you could say before your build, install some packages that you might need, or run some configuration that's necessary. And most of these systems will just provision the machines as you push up your code, and will have software you need ready to run on them, such as a particular Ruby version. So as we moved from 10 contributors up to 60, we used a managed provider called Solana Labs. They worked actually really well for us for about 2 years. They were hosted machines that would automatically detect, based on a couple of clues in the repository, what dependencies we would need installed. We had a couple of hooks that installed some binaries that were necessary to run our tests. And one of the best things about Solana Labs is out of the box, we got some strong parallelization primitives. So automatically, it would detect all of our tests, parallelize them over about 12 machines, and that was something that we didn't have to do any configuration for. While this worked well for us for quite a while, it ultimately became very expensive. So if you think about CI, most CI providers will bill you by the month. But actually, you're really running CI for maybe 8 to 10 hours a day during working hours, and at night, your load is actually very low if you have any at all. On the weekends, it's the same story. So you're paying for all of your CI at all times when you really only need it for maybe 60 hours a week. Finally, as our app grew pretty large, a bunch of the optimizations we wanted to do, such as having some software ready to go as soon as the machines booted up, we weren't able to get fine-grained control over. Our build started to grow to about 35 minutes. As the team grew, we were getting a lot of changes queued up, and ultimately we were seeing infrastructure flakiness just due to the load that we were putting on the external provider. So once again, we set out for a way to get our build times back down and enable our pipeline to move smoothly. And we came across a pretty innovative CI provider called BuildKit. So BuildKite only provides the CI scheduler portion of a CI system. They have a model called Bring Your Own Compute. So BuildKite will host a managed product that connects with your SCM provider and schedules your workload, but it's up to you to run their open source agent on your own infrastructure to pick up work that they've scheduled. This gave us a lot of flexibility to run our own software, to build pipelines without needing to build any of the UI or the other portions needed for a CI scheduler, and allowed us to keep costs low by optimizing for providing power during the day and bring up the compute during that time. So here's a basic overview of what the BuildKite architecture looks like. So if you see up here at the top, in their hosted platform, they provide the BuildKite web UI, any integrations you might expect, like with Slack or with your SCM provider, and that will start queuing the workload that your agents will run. As you go down across the bottom line, the on-premise is what lives in your own VPC. So we're running these agents on machines that we provision in AWS, and because these live in our own VPC, we can lock down access to things like our source code, any internal systems that they need access to, and any other sensitive resources that we want to access during our builds. So today, we've been using BuildKite for about a year now, and we're really happy with the system we've made. So together with BuildKite, Docker, and AWS Autoscaling groups, we've built a system that scales up, runs the tests we need to, and gives us the flexibility to put more instances in there to parallelize as the apps grow. Given that we have the scheduler portion from BuildKite, we're required to build out the compute portion of the CI. We had a handful of requirements when we set out to build this system, and the first and foremost thing we wanted to have the system be was container-based. This gives us a strong contract that applications can conform to, so every application can define a Docker file or some other method of building a container that describes all of the dependencies that they need. This gives the application developers a contract to say, I can provide you a container, and all our machines had to do was run that container with the tests. We wanted it to be auto-scaling. Being a small, leveraged team, we really couldn't afford to sit and babysit and scale up when we needed to and scale down manually. So we wanted to rig up all of the load to report those metrics to CloudWatch so our instances would come up when they need and come down when they need to. We wanted our system to be immutable. This gives us a lot of stability guarantees because we know that when tests are being run, none of the software underneath is being changed. This also gives us the ability to do canary deploys and kind of see how a new release performs before rolling it out to the entire cluster. And ultimately, we wanted it to be self-healing. We wanted to be able to identify machines that were misbehaving or not running tests well and automatically replace them with healthy instances when that happened. So we use Docker for our contract with running tests. One of the great things about this is on the infrastructure side, we simply had to provide a Docker daemon that was available, and developers could use that as they pleased. So every application will define a Docker file, and they can install any dependencies that they need. No longer does anyone have to come to an infrastructure engineer and ask to install the latest version of Ruby or install the database that they want to use. They can simply make that changes in the repository and see it instantly reflected in CI. Another great benefit of this is that it's very reproducible. So if there's a particular failure in CI that they're unable to reproduce on their host machine, they can build the container locally and run the exact same command that's running in CI to debug and get some further insight. Also, because we were trying to parallelize our tests across even more machines, we really wanted the artifacts to be portable. So we could build the image once and then ship it out to 30 or more machines for them to run all in parallel. At Gusto, for some of our larger applications, we've actually outgrown the traditional Dockerfile way of building containers. One of the nice things is that Docker provides a lower level API where we can customize for build speed. We wanted to make sure smaller changes that didn't affect things like your bundle dependencies or your database would start up really fast. And we have the ability to get down to the nitty-gritty details with Docker's APIs. AWS autoscaling groups are really powerful for defining how we want machines to come up, how we want them to be secured, and to provide workload management in a way that doesn't require much human intervention. So we define one autoscaling group for every queue that our CI system provides. This usually maps one-to-one with an application, so if on a particular day our monolith has a lot of builds, that can scale independently of some of our smaller services, and we wanted to actually manage these all in the same way, such that if we made a change to the base autoscaling group configuration, it would be reflected across all of them. So listed here are a few of the things that we use to set up our autoscaling groups. We use security groups to make sure that our build kite instances can only talk to each other and have no access to our production infrastructure or anything else in the system. So that communication is blocked at the network layer, and we can feel confident that our testing system is not going to adversely affect anything else in our VPC. We use IAM profiles to allow certain queues to have elevated permissions against AWS resources. So most of our queues need access to S3. They're just going to store some things like build artifacts and other things necessary to run the build. But we have a handful of queues that actually will spin up an instance, run a configuration against it, and assert that the machine ended up in the state we expected it to. At the end of the test, it'll spin down that instance, and in order to achieve that, we wanted to allow only that queue the elevated permissions to create and destroy EC2 instances. We use Amazon Machine Images for provisioning the software we need to run. That includes the Docker daemon, the build kite agent that I was talking about earlier, and we wanted to have a single AMI that we can use for all of our build kite machines, even if different autoscaling groups were going to listen on different queues. So this is where launch configurations come in. So each autoscaling group will define a launch configuration that says, I would like to listen to the default build kite queue or the chef build kite queue. So when the launch configuration gets executed, when the machine is brought up, it'll update the configuration of the build kite agent, and we can use that same AMI across the entire cluster, but have each autoscaling group listen to a different build kite queue. For our alarm triggers, we report some custom metrics to CloudWatch in order to know when we should scale up and when we should scale down. So we have a separate service that is querying the build kite API for the number of jobs that are queued to be run and the number of available agents that are there. We combine these metrics on a per queue basis and create something called agent utilization, which is just a percentage value of what's free at the time. When we get around, I think, 85% utilization for more than 5 minutes, we scale up, and we actually can do tiered scaling. So if for whatever reason we get a huge burst right at the beginning of the day, we can scale up twice as fast to make sure that we can handle that workload as it comes in. Also, when we start lowering down to maybe under 50% utilization for 15 minutes, that's where we start scaling back our queues. We heavily use spot requests for our auto-scaling infrastructure. AWS makes it super easy to configure what you would like your spot request bid to be for a particular auto-scaling group. So spot requests allow you to bid on an instance type, and usually get it for a fraction of what you'd pay for an on-demand instance type. Usually we set this to be pretty high, maybe pretty close to the on-demand price, and occasionally the spot market can fluctuate in such a way where you get priced out of your instance. So you're not guaranteed to have that for the duration of the hour, but we've built in a few mitigation strategies, so when we know we're going to get an instance taken away, we can cancel the job and re-queue it to be picked up by a new machine that we have in the cluster. And then finally, we really wanted to make sure that when we were scaling up and down our instances, that we were never cutting tests off and providing an unactionable error to the user when they were looking at their test results. So we use Lifecycle Hooks for this. When an autoscaling group queues a machine to be taken out of rotation, it puts it in a terminating wait state. Every instance has a service that is querying the AWS API, and when it realizes that the instance it's running on is in terminating wait, it sends a signal to the build kite agent. The build kite agent receives that signal, and it says, I'm going to finish the work I currently have, but I won't take anything new when I'm complete. It exits after it completes the job it's currently running. We then query for all of the build kite agents running on the system, and once there are none, we tell AWS to continue shutting down the machine, and it's taken out of rotation. This is really powerful because we know that we're not dropping any jobs whenever we're rotating a machine or scaling down, and can ensure stability for the test results. So managing all this configuration can be kind of complex. We always want to make sure that we're representing our infrastructure as code. For us, we use HashiCorp's Terraform to do this. So Terraform allows us to represent all of the resources you see here as modules that they provide, and we can create an abstraction on top of this. So we created our own internal module called Build Kite Autoscaling that holds all of that configuration with a variety of parameters. If you want to add a new queue, all you have to specify is the minimum size of your ASG, the maximum size of your ASG. If you want to override the instance type, you can do that, and tell us what queue you're wanting to run on. So with about 5 lines of configuration, anyone on the team can add a new queue and put a pull request against the infrastructure team, and we can apply it for them so they have it right away. So during our daily peak, we have quite a few machines running. We've got about 375 C4 2x large instances running during peak times of the day, and that gives us access to about 3,000 cores and 5.6 terabytes of memory to run tests against. On average, we're running about 9,500 jobs per day. Previously, I mentioned we run about 600 builds per day, and each build can have anywhere between 3 and 35 jobs, depending on how much they want to parallelize their test runs. Every job can spin up just the app container, or often it'll spin up a database and something like Redis in addition, and we're actually booting 22,000 containers per day. So this amounts to about 2,800 usage hours every day. If we were to use on-demand instances, this would actually get pricey pretty quick. We would pay about $1,100 or $9.20 per developer per day. Because of our use of spot instances, this is actually dramatically lower. We spend around $310 or $2.60 per developer per day. We keep a big eye on this metric. This is our signal to know that even if our total cost goes up, as long as it's growing relative to the engineering size, that we're in good shape and we can continue to scale. So immutable infrastructure is an approach to managing services and software deployments on resources wherein components are replaced rather than changed. An application or service is effectively redeployed each time any change occurs. So the way we apply this with our autoscaling groups is by building immutable AMIs. So we use Chef internally for defining our software configuration as code. So in Chef, we'll define a resource, and Chef is just a Ruby DSL for defining what packages you want to install, what configuration files you want to write down, and then pretty much anything you need to configure an instance. Once we have a change we want to make to Chef, we do the same process we saw before. We'll check out a feature branch, we'll run tests against it, and once it's code reviewed, it gets merged into development branch of Chef. At this point, Packer takes over. So whenever we run a build on development Chef, Packer will spin up a new EC2 instance, run Chef against it, and save the result as an AMI. At this point, the AMI is pushed up to the AWS registry, and it's available for whenever we want to bump the AMI we're using on our autoscaling groups. So when we're ready to actually release something, we go into Terraform, and we ask Terraform to look for the latest AMI that's available for BuildKite, for example. Terraform will tell us the AMI that it finds, and we can apply that change to our autoscaling groups to then start using this new AMI that we've built on any new instances that come up. So at this point, if it's in the middle of the day, say we have 150 instances already provisioned, we've upgraded our autoscaling groups to use the latest AMI, and at this point, all of the existing instances are left intact, and only new instances that come up will have this new AMI. This gives us the opportunity to do somewhat of a canary deploy. So as those new machines pick up work, we can monitor them individually and make sure they aren't having elevated errors or anything else that signals that those machines are unhealthy. If they are, it's pretty easy for us to roll back to the last known good AMI and then just replace all those new machines that came up that weren't behaving correctly. If we ever want to deploy a change across all of our infrastructure and get it out in a timely manner, we built a small deployment tool that allows us to mark every instance using the old AMI as unhealthy. So the autoscaling group will see that it's unhealthy and that it should be replaced. And due to the lifecycle hook configuration we've specified before, it'll allow us to wait until all the tests that they're running are complete and then gracefully shut down the machines and replace them with the new AMI that we've just rolled out. So finally, we wanted our cluster to be self-healing. So we built a small health check server that lives on the instance, and this health check server will query for the status of the BuildKite agents, the status of the Docker daemon, and a couple other critical services we have on the box. Because these machines don't traditionally respond to HTTP, we're not routing traffic to them. We have an external service in AWS periodically checking the health check server on every box. If the machine responds unhealthily more than once per minute, it's automatically taken out of rotation, and the autoscaling group will manage pulling up a new one to replace it. Additionally, when we're running tests, we always want to make sure that the user has an error that's actionable for them. So if a user sees in their test result that it failed because the Docker daemon failed to respond correctly, there's obviously nothing they can do about that. So we've built some small wrappers around our test runners to detect when there's an infrastructure error causing a test failure. When it does that, it'll swallow that exception, queue it up to be retried on a healthy machine, and provide the user with some actionable feedback that they can fix the test for. So taking a look back at what we accomplished, about a year ago, our test times were creeping up above the 35-minute mark. We were paying about $180,000 per year for this infrastructure. It was unstable. It was becoming a little flaky with the load we were putting on it, and we didn't have any options to customize the software on it to make that more stable. This was good for us when we were in the 50 to 60 range, but as we grew to a team of 120, we knew this wasn't going to support us. So fast forward to the present, and our builds are running in about 12 minutes. We're spending about half the money that we did a year ago at $90,000 per year. We've built in a lot of stability and automatic retry features that have been keeping this scaling well for us, and it's suitable for a team our size, and as we continue to grow, we feel that this will scale well with us. So looking ahead, at peak load, we're running about 375 machines, but the way we've configured it, it should be easy enough for us to press on the gas, increase the parallelization for our tests, and add more instances as the team grows. So thank you, everyone. I'll be hanging out at the startup bar. If you guys have any questions, I would love to chat with you about some CI.
Thank you very much.